Thanks for being here. I want to see a show of hands if you're familiar with Transverse Flux. So, yeah, almost half the folks here. And has anybody actually implemented a Transverse Flux machine, motor, or generator in their system? Got one. All right. Good to see. Okay. I started working on Transverse Flux in 2007, so coming up on 20 years. This technology has been quite an adventure for me personally. Happy to share with you about the state of the technology. All right, we'll cover the history of Transverse Flux. We'll talk about this as a concept that's not new, but the commercialization side quite new. We'll talk about why it's taken 130 years to get to this point. We'll compare Transverse Flux to axial flux and radial flux, and then we'll go through some physics, hopefully not too boring there. Then we'll talk about commercial applications and some experience we've had there, and some different examples, and I'll try to cover some questions, and also have time at the end for questions. All right, a little bit of a timeline in history. In the 1890s in London, there were these 250 kilowatt single-phase transverse flux machines that were running the lighting systems in many of the buildings in downtown London. So after this, Tesla took over and three-phase came in and transverse flux kind of went into the back seat. All right, so about 90 years later, perhaps, not a lot in between in terms of the patent space if you do a search, but about 90 years later, Herbert Wey in Germany was working with the Voith company, and transverse flux machines, again, will show up in the patent space. You're going to see things with lots of puzzle pieces, not necessarily something you'd want to manufacture in volume, but there were some hybrid buses that were made, to my understanding. And then in the 2000s, at the Newcastle University in the UK, there was a partnership between Professor Alan Jack and the Höganäs company out of Sweden. And there were some all SMC transverse flux bike and scooter motors. And in fact, you will see a scooter motor if you visit the folks at Alvier here. Again, kind of quiet after that until really now. So the last few years, there's been significant, really an explosion of transverse flux in terms of coming into some mainstream applications in the industrial side. But why did it take so long, and what's so challenging about this technology? The first thing is it's a 3D flux path. So you can't use spreadsheets and all the tools that are so effective in the 2D world of radial flux really doesn't apply for transverse flux. You need a true 3D FEA software. That's certainly gotten a lot easier, even in the last 15 years that I've been working with this technology. The other thing is these things are complicated to make, and there was a lot of investment that had to happen from a DFM standpoint. All right, so a quick review of the different topologies. Radial flux, so this is the ubiquitous incumbent. The flux motion is parallel to the rotor motion, hence the term radial flux. Axial flux, similar in that it has flux motion parallel to rotor motion. The advantage of this technology now is you have increased gap shear area per motor volume. So you can put more motor and steel on the gap per motor size, so advantages there. Newer technology, adoption growing, lots of activity in that space. But in both of these systems, these machine types, you have to wrap the copper through slots in the stator, whether it be axial flux or radial flux. We'll talk more about that. Transverse flux then, the most recent technology, the flux actually moves transverse to the motion of the rotor, which is where it gets its name. And the key thing here with this technology is you decouple the electrical circuit and the magnetic circuit, at least from a space sharing standpoint. That enables you to go to exceptionally high pole counts with very low coil resistance. All right, some physics. We're going to start with Faraday's law of induction, and the key here is that basically power is proportional to change in magnetic flux over change in time. And we're going to focus on the denominator, and then we're going to talk about well, actually, we'll focus on the numerator, and then we'll focus on the denominator. So then we're all familiar with the term voltage constant, or KE, in the motor, which is now including the rotational speed. Then if we do some substitution, we add in pole count. Now we see that electrical frequency, as we would expect intuitively, is proportional to the pole count and the rotational speed. All right, so conclusion of this first part here is really that KE, which is directly proportional to KT, is equal to some constants and flux times frequency, which is really just poles. So you have poles and you have flux. Those are the two things you can manipulate in that equation. And I'll say for those that actually specify motors, if you are in a lower speed application, and by that I'm going to say things under 5,000 RPM at this point, you really want to be using motor constant to your advantage. So K sub m, the motor constant, is a proportionality between the motor's ability to make torque divided by the downside, which is the resistance in the coil. And the reason that's more of a factor for lower speed machines is because your hysteresis and eddy current losses have not begun to dominate the total loss budget for the motor. Again, if we do some substitution, we're going to get to a K sub m, which is proportional, or motor constant, which is proportional to flux, poles, and resistance. So numerator, things we want to maximize. We want to maximize pole count, and we want to maximize flux. And we're going to talk about those two options. Then our enemy is the thing in the denominator. Okay, so the resistance of the coil is what we're fighting against as we're increasing the frequency of the machine. So let's talk about the first option. So we're going to work on this flux option. We're going to increase flux. Well, unfortunately, we run into some physical barriers there. The first thing is saturation density of the steel itself. And there are different material options. So somaloy, which is a material that is commonly used in transverse flux machines, unfortunately does not really offer better saturation density compared to lamination steel. So it has other advantages like its isotropic flux motion behavior, et cetera, but really doesn't offer anything in terms of pushing out the flux density. So conclusion here, we really cannot directly increase the flux that's moving through the machine. And that's key because then it pushes us into this, well, what if we could decrease the denominator? In other words, what if we can switch the flux faster? And just to quickly talk about this from the standpoint of something that you could do at home with your favorite voltmeter and a loop of wire and a magnet in your hand. Just maybe so this is a little more intuitive. If you imagine a loop of wire connected to a voltmeter and you have your magnet and you pass that magnet over that loop of wire, you're going to see a voltage, okay? So now you want to create more voltage. What can you do? Let's say more average voltage. You have two options. You could get a bigger magnet and you could move that over the wire, or you could move it faster back and forth. Those are your two options. That's really what we're talking about here. Bigger net magnets really aren't available to us in terms of per motor volume. But there is an option for increasing pole count. So this is a study done by the ETM company where essentially simulations are done with a given motor size and increasing poles from 4 to 16 and 64. And you can see what's happening to the torque, which is the solid lines, and the power, which are the dashed lines. So the torque is increasing proportional to the pole count, and it's not increasing incrementally, it's increasing dramatically here. The power is actually coming down because RPM, capability of the machine, you can see is also coming down. So this isn't a technology necessarily that's there to create ultimate power density, but from a torque density standpoint, it's for sure the biggest lever you can move. So then the question is, and I think in this audience, this is very well known, but aren't all motors kind of about the same pole count? Well, until recently, yes, that was true. So a couple of examples, these are some larger machines up in the 40, 75 horsepower range. Radial flux machines, they're still making 4 to 8 poles. And these are machines that are operating typically in hundreds of RPMs in this case. This is for a direct drive axial fan. Transverse flux machines in those power ranges, maybe 50 or over 100 poles. So dramatic, 10 to 20x more poles. So yeah, they're not all the same, not anymore anyways. So what about the other technologies? And we'll focus on radial flux, but for the most part, the trade-offs are the same for axial flux. Why can't we just increase the pole count with radial flux? This is what we refer to as the uphill battle. So again, we're sharing space between the steel and the copper, and the more slots that we put in the stator, which generally increases with pole count, the more we're sharing that space between the steel and the copper. And the other thing that's happening is we're making the path of the electrical conductor, the coil, longer and longer. And what happens as we do that? The resistance goes up. It turns out that even with a kind of a favorable approach to that modeling, you're going to see that by doubling the pole count or doubling the slots in the stator, you're going to get more than double the resistance. So yes, you've increased your numerator, but at the same time, you've increased your denominator and really aren't in a better place. It's also a thing that's happening within, especially the radial flux world in distributed windings, also during concentrated windings, that's end turns. End turns are basically non-working copper that are just completing the electrical circuit to get back to the next place in the steel where the copper can work. These don't exist in transverse flux. Here's what happens in transverse flux, which is something that has this term free optimization of pole count. So if you've got 20, 40, 60 poles, you can see the coil, which is this, let's see, I have a pointer, this piece right here. The coil is independent of the pole count. You can see the stator teeth are increasing, decreasing in pitch, increasing in count, and then the magnets and pole pieces in the rotor also increasing. Again, keep in mind, K sub M is the goal here. The coils that you'll see in a transverse flux machine look like they're out of maybe an inductor, a mechanical brake, electromagnetic brake, that kind of thing. Yeah, so they don't change with pole count. You'll have 3 of those in a 3-phase machine, 3 of those coils. This is a cross-section of a transverse flux machine, so we've sectioned through here laminations. And just want to mention that slot fill is kind of a secondary factor. It's not something that often comes up in conversations in a real-world application. But within the radial flux world, not even including the end turns, slot fills might start to max out around 70%, maybe better if you start going to rectangular wire cross-sections. In TFM, those numbers can be much higher, so it does a better job of basically putting copper in the slot. Okay, so now we can increase pole count independent of coil resistance. And again, this is a study that was done by the ETM company where they took a radial flux machine, which is represented here, and these are normalized radial flux, transverse flux by size, motor size, magnet content. And radial flux, again, as we talked about, it's this uphill battle, really does not do a very good job of increasing motor constant by increasing pole count because of the resistance going up. Then transverse flux, which is here, again, able to just freely increase K sub M as a function of increasing pole count. All right, to take a closer look at what's happening inside the machine. So this is kind of a simplified flux path here. There's still an AC current waveform moving through the coil, just as you'd expect. And we've simplified the flux motion into a spiral. The reality is it's more complex. I'll show you that. And if you want to play the next video here. So then now if you're going to make a 3-phase machine, you're going to stack 3 of these in an axial direction. So now the phases, instead of being distributed around the circumference, are distributed around the axis of the machine itself. And these can exist in 2-phase, 3-phase, 5-phase, whatever the application desires and the power electronics are prepared for. All right, and let's see, you can go ahead and play these videos. So in terms of flux motion, again, what's different here, you're watching an outer rotor, so poles are passing by stator teeth, and there is flux moving around the lamination steel here, encircling this copper coil or aluminum coil in the center section here. And then again, if you take that and multiply that out into 3-phase, now you're talking about pulses of torque that happen A, B, C, A, B, C. So instead of a radial flux machine where your torque pulses are A, B, C around the circumference, these pulses are axial and repeating back and forth. Okay, you can advance it. All right, let's talk about applications. We have some things that are basically servos that are pumping, driving axial pumps. We have rotational motion control that's happening, underwater marine propulsion, large fans, including this style here, high volume, low speed fan. So let's tell a couple of stories around these products. On the left side, that's a double diaphragm pump. It looks like the video turned off, but double diaphragm pumps are ubiquitous in many factory spaces for moving fluids. The vast majority have been and still are driven by air compressors. Huge losses, a lot of energy goes into the air compressor that you lose by dumping that pressure out into the atmosphere. There have been many efforts to electrify those systems, and the Graco company, who is parent company of ETM, Transverse Flux makers, actually was able to electrify that by putting the motor inside the casting. It drives a ball screw. Then this example over here, we're seeing a transverse flux machine that replaced a 30-to-1 gearbox with direct drive. So it was a permanent magnet, brushless DC motor, spinning at whatever 1,000 RPM, double-stage helical gearbox that was replaced with a transverse flux direct drive 60-pole motor. So quite dramatic system change there. You can advance that slide. For some reason, I'm not able to. Oh, that's never what you want to see. All right, technical difficulties. I think we're doing okay on time. There's not that many of us who could gather around my laptop. All right, so looks like we're back up and running. So again, I mentioned commercialization picture really has changed for transverse flux, especially in the last 5 to 7 years. This is a factory in Minneapolis within the Graco company. You're seeing transverse flux motors made in significant volumes there with significant automation investment in this as well. You can see the coils. These are overmolded coils, stator assembly. All right, so we're just going to rock through some examples here, and I think I just want to kind of communicate that this technology is not in some specific form factor. That question comes up often. Not in some specific performance configuration or specification range actually has quite a bit of variability in terms of what it can offer. So this is an inner rotator. Interestingly, if you look at the RPMs here, looks like you're missing a 0, right? So this motor is optimal, performing its optimal efficiency at, down around 200 RPM. So quite exceptional, low speed performance curve. The other thing you'll notice is just 120 Newton meters in a package this size for continuous stall torque. Again, exceptional. Now we're talking about the motor we saw on the paint sprayer earlier. This is a roughly 40 Newton meter stall motor, and again, making its best efficiency and operating at the 200 to 300 RPM range. Inner rotator version here, so again, you can see the different form factor that's available with this technology. Now we've got a motor that's optimized at 1,000 to 1,500 RPM. These are all neodymium magnet designs, by the way, inner and outer rotators. I've seen transverse flux be basically equal between those two approaches. Now we're talking about a small motor, so 44 millimeter diameter, all right? And this is a motor that runs much higher speed. Now we're talking about something that's optimized for 3,500 plus RPM. Also using neodymium magnet, still has 30 poles, so a 30 pole motor this size. Again, not something you see every day. And then now we're moving into ferrite designs, and especially in the last 6 months, as I know we have all seen, there's a definite uptick in ferrite-based transverse flux. So this is a machine, again, that's 600 to 800 RPM, optimized maybe up to 1,000 with ferrite. This is a high-speed ferrite design. This is something we've been calling TFM 2.0, kind of the next generation stator concept. These transverse flux motors have actually been manufactured in prototype volumes and tested in numerous locations, showing these efficiencies. So now we're talking about a, say, 3,000 to 4,000 RPM motor, all ferrite, 4 kilowatts. And again, if you're calibrated to power per size, we're talking about some fairly compelling power density with a ferrite magnet. All right, I'm going to try to answer some FAQs, and then we'll have a quick time to talk. So TFM adopters tend to value moving to direct drive, in other words, eliminating transmission components, smaller, lighter motors, better system efficiency, getting rid of rare earth materials, as we just talked about. In some cases, I've seen applications move from liquid cooling to air cooling. And in terms of the best fit applications, they tend to be high duty cycle. So let's talk about, this is an S1 load. So fans typically fall under this category where the RMS torque is basically equal to the peak torque. This is a very common application for transverse flux. So it's a cyclic load, might be an actuator, might be a pump. But still, the RMS load is over half the peak. Once you move into the category of fairly low average torque as a function of peak torque, much less likely to be a transverse flux application. All right, and then just in terms of performance envelope, I've seen machines between 3 Newton meters and 4,000 Newton meters, very low speeds up to over 5,000 RPM, and voltages very similar to low voltage systems that are out today with other technologies. All right, so does this require a special VFD? The answer is no. Rotor sensing, yeah, lots of options there. Basically, it's the same as any other servo type. Is my motor operating frequency going to be high? Commonly comes up, gosh, you got all these poles in this motor. Am I going to be switching this thing at 3 kilohertz? The answer generally is not really unless you want to. So here's a table with a number of different TFM motor types, their pole count, maximum RPM, and their operating frequency. There are many TFM motors that don't run over 200 hertz. If you want to go higher frequency, that's an option. Is it noisy? Well, oftentimes it's eliminating transmission components, and so it's actually significantly quieter than the system it replaces. And it has been commercialized into a number of sensitive, people in the room type applications. That said, if you have exceptionally low cogging torque requirements, 1%, 2% peak to peak over rated, that may be a challenge for TFM. It's not inherently smooth, but neither is radial flux. It just took a lot of years to figure it out. All right, power factor. This comes up as well. Power factor basically is similar to other permanent magnet motor types, often mid-80s, mid-90s at rated power. And it's really a design input, so there are features that can be adjusted within the motor for power factor. And cost. So cost is always complicated. It really depends on a lot of different factors, such as volume in the application and things like this. The key thing to remember with transverse flux is the material content should be significantly lower, so you should end up with lowest Newton meter per dollar, certainly in terms of material content, and assuming that the manufacturing process is straightforward, which of course is key for this technology, your total all-in cost of Newton meter per dollar should be lowest. In some cases, you're eliminating drivetrain components and the associated cost with that. Downside is limited sources of supply. You can't go to your contract manufacturer and ask them to quote transverse flux, most likely. There are also a lot of active patents in this space, given that it's a new technology, so you may be needing to license that technology. So what's the downside? It may not be a technical fit for you if the duty cycle isn't appropriate. Maybe you have exceptionally low NVH requirements. Difficult to design. It's really tough to bring this into an existing motor design team and expect to get very far very fast. It's very active from a patent standpoint. The good side there is, the upside is you can license this technology and you can commission custom designs. Again, we mentioned the supply base, another potential downside of the technology. So in summary, it's been successfully commercialized in a few different markets. High volume manufacturing is happening. Technical fit, we talked about that. It's been able to direct drive systems with up to 30-to-1. We didn't mention reliability, but many systems in the field in a lot of different environments. And I think I'm out of time. So yeah, if you have questions, feel free to grab me afterwards. And I actually brought some transverse flux motor parts if you want to see what the motors look like on the inside. All right, so thanks for your time.